Now, the reasoning in going from Cartesian coordinates to spherical coordinates is very much follows the same reasoning in going from Cartesian to cylindrical coordinates. We're just working with a different set of base vectors. Again, the objectives that you have after viewing this video are to explain how the base vectors in spherical coordinates change with position in the spherical coordinate system. And then you'll also develop the ability to compute these different differential operators in spherical coordinates. What I'd like to cover primarily in this video is a definition of spherical coordinates, and I'll sketch this out so you can have a picture of what they are geometrically. So again, starting with our fixed or invariant set of axes, the XYZ axis, and we have our general point, and just to show you where that is relative to the XY plane, and then of course to the Z axis. And here our position in spherical coordinates is given by rho. If I can get the right color pen here, rho. So rho is Greek for r, and rho is the distance from the origin. And if we were to project rho down to the xy plane, it would make an angle theta from the x-axis. It's the same theta as in cylindrical coordinates, and it is also rotated down from z by angle phi. So in spherical coordinates, point P is given by rho, theta, and phi. And so going from Cartesian to spherical coordinates, we have that the distance from the origin, rho, is just the square root of x squared plus y squared plus z squared. We have phi is equal to the arc cosine of z over rho. So you can imagine a right triangle with a hypotenuse of rho. And so the cosine of phi is equal to z over rho. And then theta is defined as the arc sine of y over rho sine theta. So the projection of rho onto the xy plane is rho sine theta. So, sorry, rho sine phi. And theta is the arc sine of y over this hypotenuse rho sine phi. And then going from spherical to Cartesian, the relationships are that x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta, and then z is equal to rho cosine theta. Now the base vectors follow the same convention that we used before. That is, E hat rho, E hat rho is in the direction of increasing distance from the origin. E hat theta is in the direction of increasing theta, and E hat phi is in the direction of increasing phi. So E hat phi is in the plane of the z-axis, the rho bar, this bar indicating rho, and it's perpendicular to rho. And theta hat is sort of going into the computer screen and to the right. If I were to draw it on the xy plane, theta hat or E hat theta would be perpendicular to the projection of this point to the z-axis. Okay. Okay, so that is spherical coordinates. And as I've written below here, I'd like to refer you to page 787 for how to evaluate the gradient, the Laplacian, the divergence of a vector, and then a curl of a vector in spherical coordinates. And that will conclude this that will conclude this video on spherical coordinates.